In this video, we'll apply equilibrium principles to acid-base titrations and buffers. Buffers are very important substances that are used in food preservatives and swimming pools and found in our blood. We can determine the acid to use in a buffer by looking at its pKa. An acid-base titration curve helps us figure out the relative amounts of acid and base and how that affects the pH of the buffer. A buffer contains a weak acid and its conjugate base. At equilibrium, both the acid and base will be present in the solution. When an acid is added to a buffer, the acid reacts with the base part of the buffer. When a base is added to a buffer, the base reacts with the acid part of the buffer. So that buffer must contain the acid and the base to resist change in pH. In the movie Titanic, this part reminded me of a titration. As the Titanic passed into the sea, the titrant passed through the burette. In a typical titration, the base is in the burette and the acid is being titrated with the base. So in this acid-base titration, 0.1 moles of base is added to 1 mole of acid. Stop the video and try to figure out how much HA and A minus, the conjugate base, are left over. So here's the answer. Note that all of the base has reacted, 0.9 moles of acid remains, and 0.1 moles of conjugate base has been produced. So here's the titration curve. Before the titration starts, only weak acid HA is present, so we can do an equilibrium calculation using Ka to calculate the pH. Once the titration starts, that is by adding base, HA and its conjugate base will be present in solution, so you can use the Henderson-Hasselbalch equation to calculate the pH in this buffer region. At the end point, all the acid HA has been neutralized, so only the conjugate base A minus is present. Use the base hydrolysis equation and Kb to calculate the pH at the endpoint. To make a buffer with a specific pH, here are the specific steps you want to follow. Let's relate a buffer to a titration curve. The halfway point is the point at which half of the original amount of acid HA has been neutralized by the base. This is where HA equals A minus and pH equals pKa at the halfway point. So stop the video and let's figure out what happens before the halfway point and after the halfway point. So before the halfway point, there's more acid and less conjugate base. After the halfway point, there's more conjugate base and less acid. So when an acid or base is added to a buffer, note that the pH doesn't change very much. However, if too much acid or base is added, eventually the buffer capacity is exceeded and the pH changes a lot. Aspirin is a weak monoprotic acid. So at what pH can aspirin be used as a buffer? Stop the video and draw a titration curve for aspirin. So here's the answer. HA represents the monoprotic acid aspirin. To calculate the pH at the starting point, look at the acid dissociation reaction. Do an equilibrium calculation using Ka. Solving for X gives you the H plus concentration and the pH turns out to be 2.2. At the halfway point, use the Henderson-Hasselbalch equation and remember that A minus equals HA, so pH equals pKa, which is 3.5 at the halfway point. At the end point, the conjugate base A minus is present, so we have to use the base hydrolysis reaction. We've accounted for dilution, which is how we get 0.05. And when we do an equilibrium calculation, X gives us the hydroxide ion concentration, then we calculate pOH, and then finally the pH. Based on the titration curve, aspirin can be used as a buffer in this pH range. You probably had milk with your breakfast this morning. Did you know that milk is an acid? The protein in milk is a weak acid, so that makes milk a buffer. When you were younger, you may have poured orange juice into your milk behind your mom's back. The curds that formed is cheese. You're a cheesemaker. There's a lot of chemistry involved in making cheese. Note that there's 400 flavor compounds in cheddar cheese. Here's a cheese making method if you're interested. The bacteria from different body parts can be used as a starter culture to make cheese. Researchers found that armpit bacteria made pretty good cheese, but not so good from the feet. And if you like your yogurt, here's what the law says. I hope you've never had kidney stones. Kidney stones form when oxalate combines with calcium ion. Foods such as spinach contain oxalate. We can determine the pH at which oxalate is present by drawing a titration curve of the diprotic acid, oxalic acid. Here's a new formula. For diprotic acid, at the first endpoint, the pH is calculated using this formula. So stop the video and draw the titration curve of oxalic acid. Make sure you label the pH at the start, each halfway point, and at the end points. And here's the answer. At the starting point, oxalic acid, we'll call it H2A, is present. Use Ka1 to calculate the pH. At the first halfway point, pH equals pKa1. At the first endpoint, use that new formula to calculate pH. At the first endpoint, the conjugate base of oxalic acid, HC2O4- is present. At the second halfway point, pH equals pKa2. At the second endpoint, we have to do another equilibrium calculation using the base hydrolysis equation. We have to account for dilution again. X equals the hydroxide ion concentration, and then finally we can calculate the pH, which is 8.4. At the second endpoint, oxalate ion is present. At this pH, oxalate combined with calcium to form kidney stones. There are also triprotic acids. Those are acids which can donate 3 protons. Phosphoric acid, which is the tart substance in Coca-Cola, is an example of a triprotic acid. So you can also draw the titration curve of phosphoric acid. This slide summarizes a triprotic acid titration curve and the equations to use at different points in the titration. For phosphoric acid, here are the answers. Coca-Cola has a pH of 2.5. This pH is in between the first halfway point and the first endpoint. So Coca-Cola will contain a little bit more H2PO4- and a little bit less H3PO4. Is Coca-Cola a buffer? I know some of you are studying biology. That means you know all about amino acids. Glycine is the simplest amino acid. So stop the video, draw a titration curve of glycine, and then you can answer these questions. Here are the answers. These are the acidic protons in glycine. This proton is lost first since it's the stronger acid. At low pH, the charge on glycine is +1. As the pH increases, the charge changes 0 due to the loss of that proton. At even higher pHs, the charge changes 0 due to the loss of the second proton. Here's the titration curve of glycine. Note that there's 2 buffer regions where the pH is relatively flat. Can glycine be used as a pH 5 buffer? pH 5 is in between the first halfway point and first endpoint, but it's still in the buffer region, so it can be used as a pH 5 buffer. The isoelectric point is the pH at which the charge equals 0. So at the first endpoint, glycine has a charge of 0. That tells us the isoelectric point of glycine is 5.97. You may have used MSG before to enhance the flavor of your food. Apply the acid-base principles you just learned to answer these questions. Go to the Objective 9 practice problem solutions to find the answers.